स्टार्ट कर दिया रिकॉर्डिंग?
हाँ स्टार्ट करो। Hello everyone. So today is week 5 of problem solving session for communication networks. So today we will be dealing with Poisson theory, and we will be dealing with the Markovian process and continuous time and discrete time Markov chain. So these will be the topics. So first let me briefly go through Markov process and Poisson process as has been taught in the week 5 of NPTEL communication network, and then I will solve some problems based on the things that have been taught today. So first I will go ahead with the theory. So yesterday in the previous class, if you remember, we have done the Poisson process. So Poisson process, if a packet arrives, if a packet arrives at a particular following a particular process which is known as Poisson, if the packet arrives at a Poisson process, then the inter-arrival time is said to be exponential, and we have from there we have derived the mm1q. So we have said that the mm1q in the mm1q Poisson process is followed for arrival, and the service is also exponential. So in this case, in the mm1q, the M stands for Markov. So what is a Markov process? So in a Markov process, what happens is, like, you consider a particular random process. So what is a random process? A random process is a random variable which is a function of time. So it is a group of random variables which follow a time series. This is called a random process, a time series of random variables. So what is random process? Random process is a time series of random variables. So at a particular time, the particular random variable, random process will have a particular value, and in the next time it will have a second value. So in the in the context of that, we have a xt. In xt gives the random variable value at time t, and it is often also referred to as xn, where xn is the random process in the discrete time domain. So a particular at a particular time, the random variable will have a particular value xt1, and in the next time instant it will have a value xt2, like that, xt3, xt4 up to xtn. So this xt1, xt2, xt3, these are called the x of t1, x of t2, these are called the states. So it is going from one state to another, like that. So what is a stationary process? A stationary process is when the random process, that is the random variable as a function of time, this is not changing. The distribution of the random variable is not changing. So the distribution at a given time t is the same distribution that is at given time t plus tau. So at two different instances of time, we have the random process following same time. That is called a stationary process. And what is an independent process? In an independent process, the particular random variable taking on a particular value is independent of the values of the other random variables. So here the value of x1 is independent of the probability of x1 equal random variable x1 is equal to small x1 is independent of the random variable values of x2, x3 and xn. So this is called an independent process. Now we come at a process which is not independent but Markov. So in independent process, a particular the random variable value at a particular time instance t1 is uh, the same as the random variable value, I mean, is independent of the random variable values at other time instance. So the value at t1 is independent of the value of t2, is independent of the value of t3. Now in Markov process there is a dependency, but the next state is not dependent on every past state. So the next state is not completely independent. So xn plus 1 is not completely independent, but xn plus 1, so the value at the n plus 1th state will only depend on xn. So x tn plus 1 x of t n plus 1 is equal to small x n plus 1. So that is at time t n plus 1, the random variable will have a value x n plus 1. This probability is only dependent, the probability of this is only dependent on the value it had at xtn. So only at the previous time instance. So if the value depends only on the previous time instance, then it is called a Markovian distribution. So the particular state value of the next state is only dependent on the state value of the current state, only dependent on the state value of the current state. So next state only depends on current state, not on the past states. So let us summarize. In Markov process, so it does not depend on the past, only depends on the current state. So p x t n plus 1, so the value of the next, this is the value of the next state, this is the value of the next state, next state. Is so the probability that x tn plus 1 is equal to x n plus 1, given that xtn is equal to xn, xtn minus 1 is equal to xn minus 1, and xt1 equal to x1. So here this is the current state, and these are the past states. So this is equal to pxtn plus 1 given xtn is equal to xn. So it only depends on the current state. The rest of the past states don't factor in the probability of the next state. So this is then if and only if xt is Markov process. So here we see that Markov process, the past is immaterial. Another concept in which the past was immaterial in the previous lecture we have covered is memorylessness. So how is memorylessness related to Markov chain or Markov process? So the relation is that this time, the time between the two states, the interarrival time, this in time between the two states is given by the exponential distribution, which is said to be memoryless. So we can go into further details later about the relation between exponential distribution, memorylessness, and Markov chain. But for now, we will be focusing on the next topic, that is a very important class of Markov chain called birth-death process. So Markov chain is a general process in which only common factor is that the next state depends only on the present. But even in this Markov process, there are multiple classes of Markov process, one of which is birth-death process. In birth-death process, basically the value of the random variables can only be integers, and they increase or decrease by 1. So if one birth occurs, then xn will increase, and if one death occurs, then xn will decrease. So this is a birth-death process. That is, in a birth-death process, the transition can take place only in neighboring states. That means if you have two xtn plus xtn is equal to 2, then xtn plus 1 can only be 1 or 3. It cannot be 0, it cannot be 5. So that is the restriction of birth-death process. In birth-death process, your neighboring states can you can only transition to neighboring states, that is increase or decrease the value of the random variable by 1. Now, discrete time Markov chain. So our next topic is a Markov chain. So in a Markov chain, what happens is that you have a particular starting state. After that, you go on to next states x1, x2, x3 up to xn, and for each of them, the only governing condition is that xn depends only on xn minus 1, or alternatively xn plus 1 only depends on xn. So you have states like this. You have states like this. So you have state like this x0. After that, you can go to x1, then you go to x2, then you go to x3. Like that, you go to xn. Now, p here the only governing condition is that p xi given for all values of I, pxi will only depend on pxi minus 1. Now here it is denoted slightly differently. It is said that pxn is equal to j only depends on pxn minus 1 equal to in minus 1. So only on the previous value. Now, this represents a transition from one state to another. So this is aptly named as transition probability. So from nth state to n minus 1th state, this is the transition probability. So if you ascribe the value j to nth state and I to n minus 1th state, then you get like this. Let's ascribe two values, that pxn is pxn is j. Let's forget about this thing. Pxn is equal to j given pxn minus 1 is equal to I. So this is called the transition probability Pij is equal to transition probability from I to J state. So like that, this xn can be equal to j given xn minus 1 equal to I. Instead of I, it can have a value L. Then the transition probability will be PLJ. So like that, for every pair of state, you will have one transition probability. And when you compose all those transition probabilities, you get the transition probability matrix. So let us say that, let's exactly follow the notation. So here you see that, here you see the transition between j from I to j is denoted as Pij. Now these so now we will introduce another notation, that is Pij, and there is a superscript n. So here we are assuming that it is going from ith state to jth state in one transition. That is, it is going from state I to state j in one transition from n minus 1 to n. Now instead of that, if it takes m transitions to get there, if it takes n transitions to get there, then the transition probability is denoted as Pij superscript n. Now now there is some derivations which we will not go through. Now instead of that, we will focus on the definition of state probabilities. We have done transition probability. Transition probability is the probability from going from one state to another state. So every state pair will have a transition probability. Now we will go to another concept, which is state probability. Now state probability is defined as the probability that at a particular time you will find the system in a particular given state. So the pi j, state probabilities are denoted by pi. Pi j is defined to be the probability that xn is equal to j. So it is simply the superscript n. So at the nth instance, what is the probability of finding the system in state j? That is the state probability. Now we will strive to find a formula between the transition probability and the state probability. We will try to find a relation between them. Now we define here pi j n as the probability that a state is at the system is at state j at time instance n. Now if the Markov chain is aperiodic, if a Markov chain is aperiodic, then the limiting probability always exists. This is a theorem. The limiting probability, that is, this n tends to infinity. So what is the at the after a very long time, say you observe a system for a very long time, it makes state transitions continuously, and then after a very long time it must come to some state and settle there. So that state is called the limiting state, and in that limiting state may or may not exist. If a particular Markov chain is periodic, then it will have no limiting state, as it will continuously oscillate between the states forever. But if it is a irreducible and aperiodic Markov chain, then it will have a limiting probability, which is given by limit n tends to infinity of this state probability. So after a very long time, the probability that the system is at state j is given as pi j. Okay. Now Now we will try to get the limiting probability or the equilibrium probability. So here we will first compose the transition probability matrix. So let us assume that there is a Markov chain. Let us assume there is a Markov chain with n states. 1, 2, 3. This is some state j, and finally n minus 1, n. So there are n states. Now this is a particular Markov chain. Now for this Markov chain, the transition probability matrix P will be given as the matrix of all the Pij's. Now since there are n states, so there will be n rows. Similarly, there will be n columns. And because it can go from any state to any state, so we will have P11, P12, P13, P1n, P21, P22, P23, P2n, dot 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 dot, and finally Pn1, Pn2, Pn3, Pnn. So this is the transition probability. And what is the state probability? The state probabilities are given as the limiting state probability. We are assuming that our Markov chain is not periodic, so it has a particular final state, and thus if it has final states, then it will have final state probabilities or equilibrium state probabilities. These are all limit n tends to infinity. Okay, so pi j limiting state probability or equilibrium state probability. Equilibrium state probability is pi j is equal to limit n tends to infinity pi j. So transition probability, so we will take the state probability vector. Since there are n states, so pi vector will be pi 0, pi 1, pi 2, finally pi n. Now the thing is, at equilibrium or at the n equal to infinity, at n tends to infinity, that is equilibrium. equilibrium, the system can only be in one of the end states. In one of the end states. So it can, at n tends to infinity, the system can only be in one of the end states. Thus, these probabilities must add up to 1. So pi 0 plus pi 1 plus pi 2 up to pi n. This will add up to 1. Because the system can only be in one of the n states. It cannot be at two states, right? So this is one condition that we have. And finally, what is pi j? Now, what is the transition probability of a particular, what is the state probability of a particular state in terms of transition probability that we need to derive? So, what is pi j? Now, pi j is that it will land at the state j. Now, if it wants to land at state j, it can be in any one of the states apart from j. So, it is at summation I is equal to 1 to n, I is equal to 1 to n, and I is not equal to j, Pij pi j. What does Pij pi j means? Pij is the probability that of transition from state I to state j. Pij is the probability of transition from state I to state j, and pi j is the probability of state j. So if you multiply them, this gives us the probability that the system was in state j, then it transitioned to state I. So sorry, this will be pi I. So the system was in state I and then it transitioned to state j. So this one was the previous probability, and then you make a transition, that is multiplied by Pij, to get the final probability. And now, since Pii is equal to 0 by definition, so a transition probability, or it cannot, actually it can, in some cases it may not be 0 also. So let's not go there. So here we can remove this condition I not equal to j, because if the transition probability is 0, then it will be handled by this Pij anyways. So if the transition probability from state I to state I, that is from a state to itself, is 0 in a particular system, then adding 0 anyways won't have any effect. And if it is not 0, then it is a valid transition and we need to include that. So we will remove I equal to j, I not equal to j condition. So pi j is simply the summation I equal to 1 to n Pij pi I. So this is the state probability definition. Now, at equilibrium, transition what is the definition of equilibrium? That transition will not happen from one state to another, will not happen. So one to another state will not happen. At equilibrium, transition from one state to another will not happen. So even if we have a particular, now we take all the states together. So we have a particular state distribution pi. We apply the transition probability vector p to it. So we make a transition, that is, we will land at the same place. So pi is equal to pi p. This is pi vector is equal to pi vector into p vector. So this is the equilibrium condition along with summation pi j, summation pi I equal to 1 to n is equal to 1. All the state probabilities must add to 1. If you solve these two, solve them together, to get state probability distribution. If you solve them together, you will get the pi's. So you will get the state probability distribution. So here we have a particular example. See, a p vector is given to be something, some matrices are there. So some matrix is there. Now you multiply, you put this equation. You put pi equal to how many states are there? 3 states are there. So pi vector will have pi 0, pi 1 and pi 2. 3 vectors. So you put pi 0, pi 1, pi 2 vector and multiply it with p, and you put in the LHS pi vector and you solve. You get these 3 equations. Now from these 3 equations, one is linearly dependent on the other. That is a redundant equation. So effectively you will have only 2 equations. Now with 2 equations you cannot solve 3 variables. That is where the third condition comes to our rescue, that is pi 0, pi 1 and pi 2 is equal to 1. This will always be true, that the limiting state probability or equilibrium state probability of all the states together will always add up to 1. So the final solution we will obtain is that pi 0 is equal to 1 by 5, pi 1 equal to 7 by 25 and pi 2 equal to 13 by 25. This is the equilibrium state probabilities. Now, if you want to do a transient behavior analysis, so these were all equilibrium. In equilibrium, that is n tends to infinity. The transitions will not happen. If the transition happen, it will remain in the same state. But if we are interested in the transient probability analysis, then in transient basically we take all the instants. So there is an initial state probability, initial state probabilities, given as pi vector 0 is equal to pi 0 0. That is the probability that a system will be at state 0 at time instant 0, pi 1 0, and so on up to pi n 0. So this is the pi 0 vector. Now, what will be the pi 1 vector? That is at time t equal to 1. It will make one transition. So pi 1 will simply be the initial probability times the transition probability matrix. This is the transition matrix. And what will be pi 2? Pi 2 will be pi 1 p. And what is pi 1 p? Pi 1 p is pi 0 p. So this is pi 0 times p times p. That is pi 0 p square. Now I think you are getting a pattern. So if you finally expand this pattern, extrapolate this pattern, you will get pi n is equal to pi 0 p to the power n. This is the transient analysis. And you can solve them together with the probability that of all the pi zeros will be the sum probability of all the pi zeros will be 1, that is summation pi 0 is equal to 1, summation at time instant 0 all the probabilities will add up to 1. Similarly, at time equal to n all the probabilities will add up to 1. So no matter what the time is, all the probabilities will always add up to 1. That is a universal law. So from these three you can solve the probability distribution. So here you can see that there is a transient. So the transient probability distribution is given like this. So we have three states at time t equal to 1, at time t equal to 0, that is initially the system was in state 0. So state 0 had a probability 1 at time instance 0. This is the time instance, this is the state. So this is the time instance and this is the state. And then we have at time t equal to 1, there is a probability, there is a 75% chance that the system will be in state 1 and there is a 25% chance that the system will be in state 2. And in the third time instance, there is these probabilities for state 0, 1 and 2. Like that it goes on. Finally at equilibrium, there is a 20% chance that the system will remain at state 0, 28% chance it will remain at state 1 and 52% chance that it will remain at state 2. So this is a transient probability distribution. This total is a transient probability distribution and this is the final equilibrium probability distribution. This part, only this column is the equilibrium probability distribution while this total chart is the transient probability distribution. Now there is Z transform of this Markov process, which is out of the syllabus. Next we go to continuous time Markov process. So in continuous time Markov chains, there are times instances t1, t2, t3, tn like that, but the main difference from the transient from the discrete time probability distribution that is given in 2.38. Let's go to 2.38 first. So here you see that xn equal to j, x1, x2, x3. So they are particular discrete time instances well defined previously beforehand. So one is x1, x2, x3 like that. But here in continuous time Markov chain, we will have times t1, t2, t3, which are in a ascending order. Only that is given, but they are not integers. They are continuous times, but arranged in an ascending order. And again, the same Markov property holds true, that at time tn plus 1, the probability distribution will only depend on the probability distribution of tn. So it will only depend on the value of tn, xtn, nothing else. So we can write it in another way, that the probability, here we have written that the probability of time is greater than s plus t given the time greater than s, that is a particular time has been spent s, and then from s a further time t has been spent by the system. So the probability distribution of a particular state at time s plus t is only only is not dependent on the expanded time s. So it is not dependent on the expanded time s, and it is only dependent on the additional time t. So from any point, no matter what, the probability distribution of s plus 2 will remain static. So you can choose to observe it from any point s. It will remain the same because it does not depend on the value of the s. So this is also called as memoryless property. So it does not really matter where it started. And with that, we will start solving some problems. After that, if we need further concepts, we can come back and we can learn more. So with that, we will be moving on to the problems. So let's go to the problem. I will is anyone here right now? Okay, only one person. Anyways, so I will give you, if you want, I will give you some time to solve after after I read the question, and then I will solve it for you. If you try and get the answer in the time I give, then you can either unmute yourself and tell the answer, or you can write in the message box. So our office has two clerks and three people, A, B, and C, who enter simultaneously. So there are two clerks and there are three people, A, B, and C, who enter simultaneously. Now these clerks will serve the people A, B, and C. So A and B begin service at the two clerks, while C waits for the first available clerk. So A and B, so it's like a bank. So in bank there are two cashiers or clerks sitting there, and three customers A, B, and C enter simultaneously. So A and B will A and B will get the service of the two clerks, while the C will get service whenever any one of A or B is finished. So assume that the service time is exponential with parameter lambda. Compute the probability that A is the last to finish the service. So A and B will begin. A and B will start the service, and then after some time, either one of A or B will finish, and then C will begin service. And here it is said that A will be the last to finish service. That is, A and B will enter together. Both of their services will start. B will finish its service. Then C will come in B's place. C will also finish it, getting its service. And after that only A's service will finish. So both B and C service has to finish before A. So here Here the time taken by A and the time taken by B is independent of each other, and the time taken by C is independent of that. So what is the probability that B will finish before A? So the probability that since these two are independent and they have the same parameter, so it is 50-50 whose service will finish first. A service can finish first or B service can finish first. So it is, wait 1 minute. So what is the first we will need to find the probability that the service time for A, that is tau A, is greater than tau B. Now since both of them have the same parameter lambda, so they are getting serviced at the same rate. So the probability that A will have a higher service time and the probability that B will have the higher service time are equal. So this will be equal to half. Now we need to find the probability that tau. Now once, let us say this event has occurred, so B has finished its service and C will come in its place. Now we have to find the probability that tau. Now tau B amount of time has elapsed because B has finished its service. Now the total service time tau A of A minus the service time of tau B. This service time is basically the time that A gets serviced even after B has finished its service. This time has to be greater than tau C. Then only A will finish last. So these two has to happen together. So tau A should be greater than tau C and tau A should be greater than tau B plus tau C. Now, because of the memorylessness property, even if tau B time has elapsed, the probability. So here we have learned that in the memoryless property, that Ps plus T given S, Ps plus T is equal to P T. So Ps plus T given S is equal to P T. So only the value of time T will matter. So if the probability that it finishes in S plus T, the service finishes in S plus T, is independent of the value of S. So it will only, given that S time has elapsed, it is independent of the value of S. So it will only depend on the time difference T. So again, this is basically half because it can be greater than 1. Both of them have a 50-50 chance of happening. So together the probability will be half into half or 1 by 4. So 1 by 4 is the probability that A will be last to finish. Let tau1 and tau2 be two exponentially distributed independent random variables with means 1 by lambda and 1 by lambda 2. 1 by lambda 1 and 1 by lambda 2. Then, so tau1 and tau2 are two random variables. Tau1 is distributed as exponential of 1 by lambda 1 and tau2 is distributed as exponential of 1 by lambda 2. So the probability of the PDF of the minimum of T1 and tau1 and tau2. So let us say that tau n is the minimum of tau1 and tau2. Then the probability that tau m is greater than some particular value t is simply, since this is the minimum, so if say tau1 is the smaller one, so if tau1 is the smaller one, then tau m is equal to tau1. Now if tau1 is greater than t and tau2 is greater than tau1, so if say tau2 is greater than tau1, let us say in one case tau2 is greater than tau1, then tau m is equal to tau1 because it is the minimum. So if tau m is greater than t, implies tau 1 is greater than t, because tau m and tau 1 are same thing. Now if tau 1 is greater than t and tau 2 is greater than tau 1, so tau 2 is obviously greater than t. So it will have to have both tau 1 is greater than t and tau 2 is greater than t. So since tau 1 and tau 2 are independent random variables, the probability distribution of one does not depend on the other. So p tau 1 greater than t and tau 2 greater than t probability is simply the product of the probability of tau 1 greater than t and the probability of tau 2 greater than t. So this will be, now the probability that tau 1 is greater than t is e to the power minus lambda 1 t, because it is exponentially distributed, and similarly this will be e to the power minus lambda 2 t. So this will be e to the power minus lambda 1 plus lambda 2 t. So the parameter is z is exponentially distributed with, this is basically t e to the power minus t by lambda. So lambda is equal to 1 by lambda is equal to lambda 1 plus lambda 2, implies lambda is equal to 1 by lambda 1 plus lambda 2. So this is, z is distributed as the exponential distribution with mean 1 by lambda 1 plus lambda 2. So the correct answer is C. So if tau 1 and tau 2 are exponential with mean lambda 1 by lambda 1 and 1 by lambda 2, the PDF of the minimum of tau 1 and tau 2 is exponentially distributed with 1 by lambda 1 plus lambda 2. Next, suppose we know that in an interval t1 t2 only one arrival of a Poisson process has occurred. Given this information, the time of this arrival is exponentially distributed with mean t1 difference t2, exponentially distributed with mean t1 plus t2, and uniformly distributed in t1 t2. So we have to find the distribution of the time of arrival. We know for one thing, let the arrival time be t. So we know for one thing that the t1 lies between t1 and t2. Let the arrival time be given as so p. Now what do we have to find the distribution of that, the time of arrival given the information that it has occurred between t1 and t2. So let the arrival be given as capital T. So the capital T is smaller than this particular value, small t, given one arrival in t1 to t2. So now if the arrival time is t, so there will be zero arrival between t1 and t, and at the moment t the arrival has come, the time the packet has arrived. So between t and t2 there will be one arrival. So we can multiply this as t, so one arrival. So it is the product of two events, one arrival in t1 to t. If it has arrived at t, Then between T1 and T there is one arrival, and there will be zero arrival between T and T2. So no further packet can come. One packet will come between T1 and T. Here T1 is included. That's why one packet will come at T1 and T. And then, sorry, not T1 is included. Here both T1 and T are included. So let us write it in a more proper fashion. So this is equal to pin one arrival in the particular T1 to T, and zero arrival from there on. So zero arrival. And divided by the conditional event, so one arrival in T1 T2. So this is basically the inter-arrival time. So since inter-arrival time is exponential, so here we will have a Poisson distribution for the arrival. So sorry, not inter-arrival, this is arrival, so it will have Poisson distribution. So Poisson distribution is lambda one arrival, so lambda t minus t1, the interval lambda t minus t1 into e to the power minus lambda t minus t1. So what is the Poisson distribution? Poisson distribution is that n packets arrive in time t is given as e to the power minus lambda t to the power n by n factorial. So here t is t minus t1 and n is 1. So lambda t minus t1 to the power 1 divided by 1 factorial. This is the first part, this part. Next part is lambda t2 minus t. Now since there are zero arrivals, this will be to the power 0 and e to the power minus lambda t minus t2. Sorry, t2 minus t by 0 factorial, which is 1. And this whole thing will get divided by lambda t2 minus t1, one arrival in t1 and t2, between t1 and t2, so e to the power minus lambda t2 minus t1 by 1 factorial. So this lambda will cancel. The exponentials, if you check, t minus t1 into t2 minus t. So e to the power t and t will cancel. So it will become e to the power minus lambda t2 minus t1, which is also there in the bottom. So this will again cancel. So these exponentials will cancel. What will remain is, this is to the power 0, so it will be 1 anyways. So what will remain is t minus t1 by t2 minus t1. So this is the probability distribution that a packet arrives at time t1. So P packet arrives at time t is equal to t minus t1 by t2 minus t. So, next is find the state transition probability of this diagram. This is very straightforward. So you just write the states 1, 2, 3 and the states 1, 2, 3. You construct the matrix and you just take down the values from the diagram. What is the probability of self transition from 1 to 1? So there is no self transition from 1 to 1. So the probability is 0. Then what is the transition probability from state 1 to 2? 1 to 2 is 1 minus p. What is the transition probability from 1 to 3? 1 to 1, say 3. This is p. Now what is the transition probability from 2 to 1? See, there is one 2 to 1 is this one. This will again have 1. Now if this is 1, these two has to be 0. You can just directly put, because at a particular time, if the probability that it will transition to state 1 is 1, then the probability that it will transition to some other states is 0. So it can be, these rows and columns have to add up to 1. Okay, so these rows and columns have to add up to 1. So because these rows and columns give us the state probabilities. So this gives pi 2, this gives pi 1, like this pi 1, pi 2, pi 3. So it has to add up to 1. Now from state 3, if you are standing at state 3, the probability of going to state 2 is, the probability of going to state 1 is 0, because see, from 3 to 1 there is no link. There is a link from 1 to 3, but no link from 3 to 1. So this is 0. And this state 3, from state 3 you go to state 2, the probability is alpha. And similarly the probability is 1 minus alpha. From state 3 to 3, that is the self transition, is 1 minus alpha. So this is the transition probability matrix. And if we see, this matches B. So the correct answer is B. Now, from the same figure, we have to find the equilibrium probability vector. What is the equilibrium probability vector? That is the pi, the limit, the distributive vector of the limiting probability distributions. And it is given as pi is equal to pi into p, where pi is the equilibrium probability distribution. So pi is, there are 3 states: pi 0, pi 1, pi 2 is equal to pi 0, pi 1, pi 2. Or let's not use 0, 1, 2. Let's use 2, 3, 1, 2, 3, because 1, 2, 3 is the notation that has been used here. So let's use 1, 2, 3, not 0, 1, 2. Pi 1, 2, 3 is equal to pi 1, 2, 3. And what is the matrix? The matrix is 0, 1 minus p, p, 1, 0, 0, 0, alpha, 1 minus alpha. So if you solve this system, let us solve this system. So first you have, this matrix will become a vector, which is pi 2, 1 minus p pi 1 plus alpha pi 2, pi 3, and then p pi 1 plus 1 minus p alpha 3. 1 minus alpha pi 3. So this is the equation. So first equation is pi 1, and we also have another equation, that is pi 1 plus pi 2 plus pi 3 is equal to 1. And we have pi 1 is equal to pi 2. We don't need to take 3 equations from here. We only need to take 1 equation. So 2 equations. So another is pi 2 is equal to 1 minus p pi 1 plus alpha pi 3. So the equations are pi1 plus pi2 plus pi3 equal to 1. Let us take it to the board. The equations are pi1 plus pi2 plus pi3 equal to 1. Pi1 is equal to pi2 and pi2 is equal to 1 minus p pi1 plus alpha pi3. So let us put pi2 here, 1 minus p pi2, because pi1 and pi2 are equal, plus alpha pi3. So p pi2, we will get p pi2 is equal to alpha pi3. And let us put pi1 equal to pi2 here. So 2 pi2 plus pi3 equal to 1. Now this will imply that pi2 is equal to alpha by p pi3. So let's put that here. So 2 alpha by p pi3 plus pi3 is equal to 1. Implies pi3 is equal to 1 by 2 alpha by p plus 1. So p by 2 alpha plus p. And what will be if this is pi3? So if this is pi3, what will be pi2? Pi2 will be alpha by p times this. So alpha by 2 alpha plus p, which will be equal to pi1. So the pi vector will be 2 alpha by 2 alpha plus p, comma alpha by 2 alpha plus p, comma p by 2 alpha plus p. So let us find the correct answer. The correct answer is alpha by 2 alpha plus p, alpha by 2 alpha plus p, p by 2 alpha plus p. So option C. Next, assume two independent processes with rate lambda 1 and lambda 2. The probability that n events occur in the first process before m events occur in the second process is. Okay, so here there are two independent Poisson processes, one with rate lambda 1, another with rate lambda 2. So the probability that n events occur in the first process before m events occur in the second process. So n events have to occur in the first process before m events will occur in the second process. Now here basically what we have to do is that we have to start with the Poisson process, and we have to independently decide whether a particular event that is happening is from the first process or from the second process. So since they are happening at rates lambda 1 and lambda 2, so what is the probability of a particular event belonging to process 1? The process 1 happens with a rate lambda 1. So the probability that it it will be belonging to process 1 is simply equal to lambda 1 by lambda 1 plus lambda 2. So of the overall rate, it will be the proportionate to the rate. Now, what we have to do is that in the n plus m minus 1 events that occur, we have to decide that we have to see the probability that if n plus m minus 1 events occur, then what will be the probability that n events of them belong to the first process. So what here is said is that n events occur in the first process before m events occur in the second process. So till n plus m minus 1th event, n events have to have occurred in the first process, and then after that, then n plus m minus 1 events have occurred, and then the next event will be for n for the second process, and then it will finish its n events. So if out of n plus m minus 1 events, n events occur in the first process, then m minus 1 events, m for Mumbai, m minus 1 events has occurred in the second process. So if m minus 1 event has occurred in the second process, then in the next event, it is certain that it is from the second process. So we only take up to n plus m minus 1. So we take total n plus m minus 1 events, and we find the probability that out of them n events belong to first process. So the probability of belonging to the first process is lambda 1 by lambda 1 plus lambda 2. Now if belonging to the first process is considered as success and belonging to the second process is considered as failure, then the probability of success is lambda 1 by lambda 1 plus lambda 2, and total number of events is n plus m minus 1, and the desired number of events is n. So we just have to get the probability, we just have to get the binomial distribution of k given the parameters n plus m minus 1 and lambda 1 by lambda 1 plus lambda 2. So with these two parameters n plus m minus 1 and lambda 1 plus lambda 2 by lambda 1 by lambda 1 plus lambda 2, this will give us the probability as summation I equal to n to n plus m minus 1 n plus m minus 1 Cn into lambda 1 by lambda 1 plus lambda 2. This will be n plus m minus 1, that is the total, minus this will be to the power I, sorry, and lambda 2 by lambda 1 plus lambda 2. The failure will be n plus m minus 1 minus I. So we see that n plus m minus 1 Ci, not Cn, sorry, Ci, n plus m minus 1 Ci into success probability to the power n plus m minus 1 minus I into failure probability to the power I. But this is success probability, so n plus this will be to the power I, and the failure probability will be to the power n plus m minus 1 minus I. So the correct answer is A, not B. Now let tau 1 and tau 2 be two exponentially distributed independent random variables with means 1 by lambda 1 and 1 by lambda 2. Then the probability that P tau 1 is less than tau 2 is. Okay, so we have to find the probability that tau 1 is less than tau 2. So probability of tau 1 less than tau 2 is basically there are, so over the entire distribution of tau 2 we have to integrate to cover all possible cases in which tau 1 will be greater than tau 2. So sorry, tau 1 is lesser than tau 2. So we have to take p tau 1 less than tau 2, given we have to take some value of tau 2 equal to say t, f tau 2 let us write in the board. Tau 1 less than tau 2, this will simply be p tau 1 less than tau 2 given tau 2 is equal to t. And what is the probability of tau 2 equal to t? Now we integrate over all such possible values of t. So 0 to infinity p tau 1 less than tau 2. So tau 1 will always be tau 2. So tau 1 will always be less than tau 2. So we integrate over all possible values of tau 2. Now if tau 2 is equal to t, then tau 1 less than tau 2 becomes tau 1 less than tau 2 becomes simply tau 1 less than t. Now since this is exponential distribution, now this gives a particular value of tau 1. Now this gives a particular value of tau 1. So we calculate the d22, yeah. So we calculate the exponential integration now. So tau 1 less than tau 2, this one will be given like this. So tau 1 less than t, this one will be given like this, and this one will be like, sorry, this is not tau 2 less than t, this is tau 2 is equal to t. This will be given as lambda 2 . So this is tau 2 equal to t. So this will simply be the probability distribution. Tau 2 with lambda 2 e to the power minus lambda 2 t. And for t1 it is less than. So it is the cumulative distribution. So 1 minus lambda 1 x minus lambda 1 t dt. Now if you do the integration, you will finally get lambda 1 by lambda 1 plus lambda 2. So this is the correct answer. I will leave the integration to you. So here the correct answer will be lambda 1 plus lambda 2. Lambda 1 by lambda 1 plus lambda 2. Assume that passengers arrive at a bus station as a Poisson process with the rate lambda. The only bus departs after a deterministic time t. Let W be the combined waiting time for all passengers. Find the expectation of W. So what is the average waiting time for a passenger? That is what is asked in this question. So all the passengers P1, P2, P3 will arrive in the time instance 0 to t. So if there are n passengers, so there are n arrivals in time capital T. So there will be n arrivals. Now if passenger P1 arrives at T1, then it waits for capital T minus T1. So if, let us take it to the board, if passenger T1 arrives at T1, time T1, arrives at time T1, it waits W1 is equal to capital T minus small t. So like that, now if between 0 and t the number of arrivals is nt, then the waiting time is if between 0 and t nt arrivals occur, EW will be equal to the summation of so here we have distributed the waiting time conditioning on the number of arrivals. Since we know the number of arrivals follow Poisson, so NT follows Poisson, we know NT follows Poisson. So we have to condition the waiting time on a known distribution. So we condition the waiting time on NT. And what can be the number of arrivals? The number of arrivals, since one thing is given, it can be between 0 to infinity. At any given time interval, 0 arrivals can occur or infinite number of arrivals can occur. So now if the k arrivals have happened, then the average waiting time of each, if if k arrivals have happened, then on an average, since this is here, on an average, a particular passenger, since the passenger has to arrive between this time and this time, so on an average, the passenger will wait. So one passenger at a particular time will arrive, have to wait for t by 2. So if k passengers have arrived, so the expected waiting time will be, since k passengers have arrived and each on average will wait t by 2 time, so this will be k into t by 2 because k passengers have arrived. Now what is the probability that k packets arrive at time t? That is this thing, nt is equal to k. If I put this thing out, then this is basically k into p and t is equal to k. This is basically the expectation of nt, expectation of a Poisson process, and we know that nt is Poisson. So this is expectation of nt, which is Poisson. So this will be, since this is Poisson, so the rate is given to be lambda. So this will be the average number of arrival will be lambda t. So the rate is lambda. So at time instance t, Poisson average arrival will be lambda t. So t by 2 into lambda t is equal to lambda t square by 2. Now the bus arrival time follows exponential distribution with parameter mu. The only bus arrival time. So the bus arrived at time t, which was deterministic. Now in this question, the bus arrival time is exponential. So what is the expected value of the combined waiting time for all passengers? Now we will have exponential waiting. So here the waiting time expectation w by t equal to t. So we know that the waiting time up to a given time instance small t. Now we have to condition it on the exponential distribution. So previously it was fixed that if a particular packet arrives at t1, passenger arrives at t1, it will have to wait capital T minus t1 time. Now here, let's say we wait for the bus arrival happens at a particular time small t. This is the time the bus arrival happens. Since the bus arrival is happening at time small t, so this small t is again distributed as exponential. And if we integrate on all possible values of small t, then we get the average waiting time. Now this is the waiting time if bus arrives at time t. So this was previously derived to be lambda t square by 2. So in the previous question we derived this to be lambda t square by 2. So we just put that is equal to 0 to infinity lambda t square by 2. And the exponential distribution follows a rate mu. The bus arrival exponential distribution follows mu. So mu to the power minus mu t dt. So this will be lambda mu by 2 integration 0 to infinity t square e to the power minus mu t dt. Now if you solve this integration, you will get lambda by mu square to be the result. So the correct answer is option B, lambda by mu square. Now you have two machines. Machine 1 has a lifetime t1, which is exponentially distributed with parameter lambda 1, and machine 2 has lifetime t2, which is exponentially t2, lambda 2. Machine 1 starts at time t is 0, and machine 2 starts at time capital T. Assume that capital T is deterministic, that is, it is known. Compute the probability that M1 is the first to fail. So, M1 has a lifetime T1, M2 has a lifetime T2. So, T1 should be less than. Now, the machine 2 will go on for time T2, and it will start at time T. So, the total time that T1 has to run for is T2 plus T. So, T2 plus T, if it fails before T2 plus T, if T1 is less than T2 plus T, then when machine 1 fails, machine 2 will still be running. So this is the required condition given by the problem. So now here the probability that it will be less than T2 plus T can be divided into two cases. That is, one is that the machine 1 fails before even the machine 2 started. And the second case is that machine 1 fails after machine 2 started. That is, T1 is greater than T, but is less than T2 plus T. So there are two cases. In one, the second machine has not yet started. In the second case, the second machine has just started. So now we condition this as T1 is less than T2 plus T, given T1 greater than T, into T1 greater than T. Now here T1 less than T, this is just simple cumulative distribution of exponential. So the probability that it is greater than T is e to the power minus lambda 1t. So the probability that it is less than T is 1 minus e to the power minus lambda 1t. So this will simply be 1 minus this part will be 1 minus e to the power minus lambda 1t. And the next part is, see, what is the probability that it will run for T2 plus T given that it has run for T? Now this is a classic case of memorylessness. So it has already run for T. So what is the probability that it will run for T2 plus T? So this is independent of T. So the T term will simply vanish because it is memoryless. The probability that it will run for T2 plus T is independent of T. So no matter wherever you start, if it has to run for T2 plus T, it will run for T2 plus T. Doesn't matter if it has run till T or not. So this will simply become the case of T1 is less than T2. T1 is less than T2. Into T1 is greater than T. So what is the probability T1 greater than T? This will simply be e to the power minus lambda 1t. And T1, what is the probability of T1 less than T2? Now we have solved this question already previously. That P T1 less than T2 is lambda 1 by lambda 1 plus lambda 2. So this will be 1 minus e to the power minus lambda 1t plus lambda 1 by lambda 1 plus lambda 2 e to the power minus lambda 1t. So if you add them, you will get 1 plus lambda 2 by lambda 1 plus lambda 2 e to the power minus lambda 1t. So this is the correct answer. So here it is written like this: 1 minus e to the power minus lambda 1t plus lambda 1 by lambda 1 plus 2 e to the power minus lambda 1t. You can simplify this further, but they have not, so we will not. The correct answer is option A. And now the same problem, but this time the starting time of machine 2 is again exponential. So here the work is even simpler. So Pt1 less than T2 plus T. Here T1, T2, T, everything is exponential. So this will be T1 less than T, or as discussed previously, T1 greater than T and T1 less than T2 plus T. So it can either, machine 1 can fail before machine 2 has started, or it can fail after machine 2 has started, but before machine 2's lifetime. So now this is, since all the processes are independent, they are all independent processes from each other, so this will all simplify to P T1 less than, this will all take be turned into a product. Now T1 less than T2 plus T, so the probability that it will run for T2 plus T is independent of T, so it is equivalent to T1 less than T plus T1 greater than T2 and T2 less than T. So if you solve like this, like previously, each one of them will be, this one will be lambda 1 by lambda 1 plus mu, this one will be lambda 1 by lambda 1 plus lambda 2, and the final one will be mu by lambda 1 plus lambda 2. So the correct answer will be, if you simplify, the correct answer will be lambda 1 plus lambda 2 whole square into lambda 1 into mu by lambda 1 plus lambda 2 whole square plus lambda 1 by lambda 1 plus mu. So correct answer is option A. So this brings us to the close of week 5 of problem solving session. Next week, Tuesday, same time, 6 to 8, we will host the week 6. Join there. For now, the class is adjourned. Thank you.